Hello students, welcome to the second session of P block elements. Before beginning, let us again go through one of the beautiful thoughts which might inspire you. It goes like this: do difficult things when they are easy and do the great things while they are small. I repeat, do difficult things when they are easy and do the great things while they are small. I hope that fires up you to do the difficult and great things in your life. Coming to B block elements, in the previous session we had discussed about the general physical properties. I hope you have gone through it. If not, please go through it. In this session, we'll discuss about some of the important general chemical properties. So let us begin. In the chemical properties, we'll first look into the general oxidation state of this group. Most of the elements in this group will show -3, +3 and +4 oxidation state. But remember, nitrogen and phosphorus shows a whole lot of oxidation state between -3 and +5. There is two important points in this oxidation state that you have to remember. One is the tendency of -3 and +5 oxidation state decreases down the group. I repeat, the tendency of -3 and +5 oxidation state decreases down the group. The reason for -3 oxidation state tendency to decrease is because when you come down the group, you know that size of the element increases, metallic character increases, electronegativity decreases. All these goes to reduce the tendency of -3 oxidation state, because -3 oxidation state means it has to accept 3 electrons. Well, now if you look into the reason for decrease in the tendency for +5 oxidation state when you come down the group, then we can say it is due to a phenomena which is known as inert pair effect. Now, what is inert pair effect? We can simply say that it is the reluctance of s orbital electron to participate in bond formation. Inert pair effects comes into play when you go down the group. So for example, in this group, when you reach bismuth, the outermost shell has got s and p orbital. In this, s contains 2 electrons and p contains 3 electrons. Since it's the outermost orbital, due to the shape of s orbital, the s orbital's electrons are strongly held. Due to the shape of s orbital electrons are strongly held, which is also said that s orbital electrons are highly penetrated. Hence, it is difficult for this s orbital electron to get into bond formation. Hence, what happens is that when you come down the group, the s orbital electrons does not participate in bond formation. This results in the restriction of the oxidation state to +3. This phenomena is known as inert pair effect. So inert pair effect can be summarized as reluctance in the participation of s orbital electron, outermost s orbital electron towards bond formation. Okay. Another important point of oxidation state is that the nitrogen and phosphorus in all their intermediate oxidation state, that is apart from -3 and +5 oxidation state, tend to disproportionate. I hope you know what is disproportionation. Well, it is nothing but it's a redox reaction in which the same elements in the reaction will undergo both oxidation and reduction simultaneously. Now we'll discuss about the covalency, ability of an element to form the covalent bond. The maximum covalency of nitrogen is 4, as you can see in the case of NH4+, which means that nitrogen is capable of forming 4 covalent bond. In NH4+, that is ammonium ion, it is in the sp3 hybridization. We can say that it has a maximum covalency of 4. Whereas in phosphorus, due to the availability of d orbitals, it can expand its covalency up to 6. Why the maximum covalency of nitrogen is restricted to 4 and the maximum covalency of phosphorus can be extended beyond 4 up to 6. It is due to the d orbitals. In case of nitrogen, there is non-availability of d orbitals, whereas in case of phosphorus, there is the presence of d orbitals. Now let us look into the type of hydrides that group 15 elements form. The general formula is EH3. So some of the most important hydrides are NH3, PH3. NH3 is, you know that it's ammonia, and PH3 is phosphine. Similarly, there is arsine, stibine and bismuthine. Among these, NH3 is the most stable and the stability decreases down the group. That means BiH3 is the least stable. Well, how can you explain this phenomena? This can be explained on the basis of bond dissociation enthalpy. See, I have enlisted bond dissociation enthalpy. In this case, it is actually the average bond dissociation enthalpy. So what is bond dissociation enthalpy? It is the enthalpy change required to break 1 mole of similar kind of bond. In case of ammonia, it is 389 and it goes on decreasing. So stability can be easily explained on the basis of bond dissociation enthalpy. Greater the bond dissociation enthalpy, greater is the stability. Another characteristic that you can explain on the basis of bond dissociation enthalpy is the reducing character. We can say that bond dissociation enthalpy is inversely proportional to the reducing character. That is, greater the bond dissociation enthalpy, lesser is the reducing capacity. It means that higher the bond strength, lesser is the reducing character. This makes ammonia a very mild reducing agent, whereas BiH3 a powerful reducing agent. Well, talking about the hydride, one of the most important character of these hydrides are their basic nature. The basic character decreases down the group. You can see that among this, the ammonia is most basic. The basic nature of these hydrides is due to the presence of lone pair of electrons. Since they can donate their lone pair of electrons, they are also typical Lewis bases. And why NH3 is most basic among this? It is because of its small size. Due to the small size of nitrogen, it has got a very concentrated, dense electron cloud, which it can donate effectively. Whereas as the size increases, size of the atom increases, the electron clouds becomes more diffused. Hence, the donation is not that effective. Therefore, among the hydrides, ammonia is most basic. If you look into the melting point of hydrides, you will see that actually the melting point increases down the group. But here there is again the anomalous property due to the electronegativity of nitrogen. Here the melting point of ammonia is much higher than that of other hydrides. So a question can be asked, why NH3 is liquid whereas PH3 is a gas? The answer is quite simple. It is because of high electronegativity of nitrogen, which makes intermolecular hydrogen bonding in NH3 molecule. Due to intermolecular hydrogen bonding, NH3 molecules come closer, hence they exist in the liquid state, whereas PH3 is a gas. Coming to oxides, group 15 element basically forms two types of oxide, having the general formula M2O3 and M2O5. But nitrogen, being the first member, it can form a whole lot of oxide from -3 to +5, and that is basically because of its small size. I have enlisted the neutral as well as acidic oxides. The first among this is N2O, which is also known as nitrous oxide, which is also known as laughing gas. Then you have got nitric oxide, then dinitrogen trioxide, nitrogen dioxide, and dinitrogen pentoxide. The first two oxides, that is nitrous oxide and nitric oxides, are neutral. As the oxidation state of the element increases, the acidic nature of oxide increases. This is one of the most important points. It is generally applicable. As the oxidation state of element increases, acidic nature of its oxide increases. Phosphorus, arsenic and antimony, they form the two types of oxide, that is trioxides and pentoxides. Among these, trioxides are more stable than pentoxide. Why trioxides are more stable than pentoxide? That is because in pentoxide, the phosphorus is in excited state. In pentoxide, the phosphorus is in excited state. Both trioxide and pentoxides of phosphorus, arsenic and antimony, they exist as dimers. These are some of the important points of oxides. Now let us look into the reactivity of group 15 element towards halogen. With halogen, they form two types of halides with a general formula EX3 and EX5, that is trihalide and pentahalide. Among these, pentahalides are more covalent. As the oxidation state increases, compounds become more covalent. Among the trihalide, NCl3 is unstable. NCl3 is unstable, whereas all other trihalides are stable. And among pentahalides, nitrogen is not capable of forming pentahalide. nitrogen is not capable of forming pentahalides. So the question might be asked, why nitrogen does not form a pentahalide like phosphorus? Well, the reason for the abnormal nature of nitrogen, in this case, it is due to the lack of d orbitals. Why nitrogen does not form NCl5? It is due to lack of d orbitals. Because hybridization in PCl5 is sp3d2. Hybridization in PCl5 is sp3d2. Since nitrogen does not have d orbital, so it is not capable of forming NCl5. Okay. Now with metals, group 15 will react to form binary compounds in their -3 oxidation state. For example, you will have calcium nitride, calcium phosphide, sodium arsenide, zinc antimonide, magnesium bismuthide, etc.